All right, we are now in chapter 6. I'm skipping chapter 5 or section 5 4 because I think that that is going to be some unrelated or a little too unrelated to just solving systems of equations. You're doing what's called linear programming, which is really incredible stuff, but like I've said before, it's a little too unrelated. So we're moving on just to study matrices. And matrices, um, we're working our way into them by studying systems of equations. So a system of linear equations looks like this. Systems of linear equations looks like 4x plus 3y equals 5, 2x minus 3y equals 1. And this is really, if I were to be super specific, a system of obviously two linear equations with two variables, right? Looks like this. And then we've studied a few different ways of solving it. We did the substitution, we did the elimination, and then the Gauss-Jordan, which involved putting it into a matrix form. So who cares? Like why any of this, right? Why am I making your lives so difficult? Well, if you get a technical job, let's say like an engineering job of some sort, you might come across a scenario like this, where you have some sort of a weight. This represents ropes. This is a diagram with two ropes here. This is, we'll call this rope 1, and this is rope 2, right? And let's say there's a weight right here, and that weight is going to pull down on those two ropes, right? If I know the weight of that object, and I think I need to know maybe an angle here that I'll call angle 1 and angle 2, and I want to define how tense, how tightly pulled are these two ropes, which I would call the tension in rope 1 is equal to some number, and the tension in rope 2 is equal to some other number. The way I would do that is with a system of equations. And I'd have to know some things about physics. If you ever take physics 1, which anybody's going to go in engineering will, or even if you go into nursing, you might run into this problem where you have to know a little bit of trig and things like that. But it ends up being that where you have a system of two equations, you plug something, you solve for one variable, plug into the other, and you end up being able to figure out the two tensions. A very simple example from a textbook, but in general, in real life, if you were to take a course in statics, you might have something called a truss. And I'm doing a very bad job drawing here, but let's see. Something like this. Here we go. There we go. There's a truss right there. And this has forces at all these different joints, and you want to figure out the stress on all those different beams, and you would need to know the strength of the material that you're working with and things like that, and then you can do a more complicated version of that problem where you're having to solve a system of equations to figure out the forces or the stresses on each of these beams, so that you have what's called static equilibrium, and so that your truss isn't moving, because you don't want to have, on a bridge, you don't want to have things, or in certain spots you don't want things to be moving. A bridge, you do want some flexibility, but and so things get more and more complicated. You imagine on a large bridge, I don't know, you might have hundreds or even more of trusses, and all those forces need to be figured out and canceled out and everything, and so you have maybe a very large matrix that you need a computer to solve. And so you stop looking at things as systems of equations. You no longer think of it as this, because the scenario's gotten bigger. You've got more things you're dealing with, and you start thinking of these large things as just matrices that need to be solved. And so that's what we're starting to do here. This is a crude example. I did take statics, and I kind of ran into this, but it was a while ago. So um, anyways, so what we're going to do now is we're going to take the matrix that we would make out of this part of the system, and we'll call it something. We'll call it M, right? And we'll talk about it. We'll talk about M as its own mathematical objects, right? And what I mean by that, we can take a matrix and define a set of operations that we can do with multiple matrices. So we can define operations. So the first operations is going to be matrix addition and matrix subtraction. Okay? Which is, these are going to be pretty intuitive. There's not much to them, but they're not the same as just adding and subtracting real numbers. They look different on paper. So second operation is going to be multiplication by a real number. In general, you would call that a scalar. There's matrices and vector spaces don't have to be just made out of real numbers, though that's often the analogy that's used. But anyways, so that's what you're going to be concerned with, though. Number 3 would be the matrix product or matrix multiplication. The book says matrix product, but same idea. So these are the 3 operations that we're going to really work with in this book with matrices, and there's one more called the determinant, but we'll learn that later. So for addition of matrices, given a matrix A, we'll call this A11, A12, A21, and A22. This is a nice organized way of labeling the elements in your matrix, because the first index here represents the row, and the second index represents the column. So row 1, column 1, row 1, column 2, row 2, column 1, and row 2, column 2. Alright, so we do that with B as well. B11, B12, B21, and B22. Right? So now we want to add these together. You might already know how to do it. It's going to be A11 plus B11, A12 plus B12, A21 plus B21, and A22 plus B22. Okay? So that's how you add together 2 matrices. So you just take the elements, you say, okay, this gets added to that, right? You wouldn't add this and B12. That's not the definition of the addition. Great. So now, as an example, we'll do example 1 on page 466. We want to add together these 2 matrices. So it turns out to be A plus W. So A, B, C, D, W, X, Y, Z. This is going to go with this. And then B goes with X, so B plus X, C plus Y, and D plus Z. Simple enough. Okay. Okay, they don't have to be square matrices. It's difficult to write everything in a nice general formula of what this is supposed to look like, so I try to do it through examples, and then you can develop the idea. So if I were to add together these 2 matrices, again, I just look at the location. 2 is in first row, first column. 3 is in first row, first column, so those 2 go together. So that's going to be 6, and then I can just go across. -3 plus 1 is -2, 0 plus 2 is 2, 1 plus negative 3 is negative 2. 2 plus 2 is 4. And negative 5 and 5 is 0. So that's my answer. Alright, what about these? Well, this is in the first row, first column. So I would think that I could just say, okay, add the first row, first column here. You're going to run into a problem. And that is that when I get to, let's say, this element here. Okay, 4 is in the first row and the third column. Okay, where's my third column over here? There's none. So this can't be done. Right? Matrices must have same number of rows and columns to do addition and subtraction. Okay? So this is an operation that's not defined, so we just say can't be done. Example 2, we want to subtract these two matrices. This is really the same thing as addition, except now there's a negative in front, so you just got to distribute that to everything. So now you would say 3 minus negative 2 is going to be 5. Negative 2 minus 2 is going to be negative 4. 5 minus 3 is 2. 0 minus 4 is negative 4. Done. Okay, so that's matrix addition and subtraction. Different than just adding numbers together, but not really super complicated. Multiplication by a number k. So given a matrix M, km, meaning k times m, is found by multiplying every element in the matrix M by k. So if I'm given k times, let's say a 2 by 2, m11, m12, m21, m22, then this would become k m11 plus, oops, not plus, m12 is k, km21, km22. Okay? So again, should be intuitive. If you don't get it, ask me in class. Alright, example 3, page 469. So we are given a matrix 3, negative 1, 0, negative 2, 1, 3, 0, negative 1, and negative 2. And we want to multiply it by negative 2. Okay, how about I put this in the camera so you can actually see what I'm doing. Okay, so there's the matrix, and we want to multiply it by that number. Again, page 469. So all you do is you multiply every element in the matrix by that number, and you get your answer. So negative 2 times 3 is negative 6. Negative 2 times negative 1 is 2. 0. Negative 2 times negative 2 is 4. Negative 2, negative 6, 0, 2, and 4. Done. There's not much more to say about that, so I won't say any more about that. The matrix product. This is really what I've kind of just rushed. I'm kind of rushing to get to because this is the more important operation. And though you might find it a little strange if you haven't seen it before, the matrix product actually preserves all of the row operations that we define in chapter 5 so that we can use it to solve systems of equations. And what I was trying to say here is we have it's a faster way of solving a system of equations, especially when things get very large. What I was trying to illustrate with that example with all those trusses if you're an engineer and you have 100 trusses, and you're the chief civil engineer, maybe, and you got to make sure everything's all um, stable and static. You would organize this into a matrix, and there's probably going to be some code writing in there and a lot more computational stuff. But the idea is back to this stuff. It's and you're not thinking of it so much as systems of equations anymore, because that's too much detail for what we want to do. We don't need to think of it as substituting everything in there. We can think of it as, okay, what's the big picture? I have a matrix A that has all these forces in there that need to be equalized, and how can I think of the operations on that now? So it's a way of kind of zooming out to solve bigger problems. Okay, and the matrix product is extremely important to be able to do that. So to understand it, you just have to do it. So we multiply, if we want to multiply, let's say, this matrix by this matrix, really you would call it a row vector and a column vector. It's going to be this number times this number. So you think of it as multiply a row by a column. Okay. Excuse me, I'm sorry. Right, this is actually example 5 on page 472. So this becomes a row vector, and it's this number times this number, so 2 times -5, and then this number times this number. Oh, it's not a row vector, I'm sorry, it's a sum. This number times this number, -3 times 2, and then 0 times -2. So this is -10 minus 6 plus 0 equals -16. So this is, you end up getting what's, I guess you would call it a 1-by-1 matrix, but it's just a number, -16. That's not always going to be the case, which we'll see here. If I want to multiply these two matrices, let me do that row column thingy again. Look, take the first row, multiply the first column, and see what I get. If I multiply this number by this number, I get 5. This number by this number is 14. So the sum of those two products gives me my first element. See? And then this by this gives me 1 times 6 is 6, plus 2 times 8 is 16. 3 times 5 is 15. So now we're doing this column and this row in the first column. 4 times 7 is 28. This row and the second column. 3 times 6 is 24. And then 4 times 8 is 32. Whoops. Alright, all said and done, we get 19, 22, 43, and 56. Okay? So that's the matrix product for those two matrices. But that row and column thinking is what gets you through it. So remember how we ran into a problem when we tried to add this matrix and this matrix. It wasn't defined because we didn't have anything to add this number to, because there's nothing over here. There's no third column. Same here. So there is a way to define it so that it actually makes sense, and that is that you have to have before I make that point, let me do another example. So let's we can do a 2 by 2 matrix multiplied with a 2 by 1 matrix. Remember, this is the row and this is the columns. This is the rows and this is the columns, right? What the point that I was getting at was that these two numbers have to match. Okay? If they don't match, you can't do the multiplication. It doesn't make any sense. And the reason is because when you're doing it, the number of rows here, as you think of the rows multiplying the columns, clearly you have to have the same number. So 2 times 1 is going to give me 2, plus 4 times 2 is going to give me 8. Okay? 6 times 1 is 6, plus 8 times 2 is 16. Here's another thing. What I end up with is the outer elements. If I compare the outer dimensions, I guess. So I was multiplying a 2 by 2 with a 2 by 1, so I end up with a 2 by 1. You see? This is a 2 by 1. That's some things to help you do a sanity check as you do these matrix multiplications. 10, 2 plus 8 is 10, and 6 and 16 is 22. Okay? So we notice some things. We can take each row and multiply it by each column, right? Multiply. It's not exactly multiplying like we used to think of it. You're taking this number, multiplying it by this, and then adding it to this number multiplied by this. So it's a different type of multiplication, but that's what we're calling it because it's analogous. So we take each row, and in the first matrix, and we multiply it by each column in our second matrix to get our new matrix, which in this case was 10 and 22. Okay. I don't know why I left so much space here. I think I was going to make a point and I forgot what it was. But number 2, what has to happen in order for us to even do the multiplication? And like I said, these two numbers in here have to match. You have to have the same number of columns in the second matrix has to match the number of rows in the first matrix, or else you can't do it. Example 7 helps us see that. So example 7 on page 474. So you have these 4 matrices that you're given, and it's going to ask you to do various products. So first one is A times B, right? Okay. So multiplying A times B, I'm going to do this row times this column. Oh, so it works. First of all, we check, does it work? Well, how many rows do I have here? I have 3 rows, and whoa, snappy, hold on. I think I've been saying things backwards. The number of columns in the first matrix has to match the number of rows in the second matrix. I think I said it backwards. See, I still get confused. So I have I have 2 columns, and that matches 2 rows. So we can do this. All right. So this times this is going to give me 2 times 1 is 2, 1 times 2 is 2, so that gives me 4 when I add it up. And then this times this is going to give me 2 times negative 1 is negative 2, plus 1 times 1 is negative 1. And you always remember that until you're done with your first row multiplying everything, that's what's going to finish the first row of your new matrix. Does that make sense? This first row times all of these columns gives me the first row of my new matrix. So it should have 4 elements. So now I do this one. This row times the third column. 2 times 0 is 0, plus 1 times 2 is 2. 2 times 1 is 2, plus 1 times 0 is 2. Okay, so I'm done making that first row. This row times every column in here will make my second row in the new matrix. You just got to practice it a lot. 1 times 1 plus 0 times 2 is 1. 1 times negative 1 plus 0 times 1 is negative 1. 1 times 0 plus 0 times 2 is 0. 1 times 1 plus 0 times 0 is 0. Last one comes from here. Negative 1 times 1 is negative 1 plus 2 times 2 is 4, so that's going to give me 3. And then 3, 4, and negative 1 if you finish. I don't want to bore you. So, again, a sanity check. What was the dimensions of this matrix? It was a 3 rows and 2 columns. And then this matrix, the second one, was 2 rows and 4 columns. These two numbers match, so we can do it. What did we end up with? We ended up with 3 rows and 4 columns. 3 rows, 4 columns. Whoops, 4 columns. So that's how that works. Let's notice something here. Excuse me. Let's try to multiply b times a. Well, let me write it out. Even though it's already written up there, I want to write them right next to each other so you could see it. 1, 2, negative 1, 1, 0, 2, 1, 0. Whoops. And then 2, 1, negative 1, 1, 0, 2. And I'm going to try to do this multiplication. So I'm going to multiply this row by this column. 1 times 2, if I were to try to make a new matrix, 1 times 2 would give me 2. Plus, 1 times 2 is 2 plus negative 1 times 1 plus 0 times negative 1 plus 1 times what? There's nothing there. So this can't be done. This is not defined. Because the rows here and the columns here don't match. This is a 2-row and 4-column matrix, and this is a 3-row and 2-column matrix. So 4 and 3 don't go together. It's not going to happen. But notice this. I have a times b, and it worked, but b times a didn't work. So a times b does not equal b times a. So in this new set or group of objects that we're calling matrices, we don't have something that we're used to having for our whole lives. We've been used to having this thing, and it's when we're able to switch the order of the numbers in the operation. So 5 times 3 is equal to 3 times 5. Obviously this is 15 and this is 15. This is commutativity. We've lost that. We don't have it anymore. It's not always true. So that's important. Now we're understanding how we have these, just like we kind of did for functions, when we would take a f plus g of x, and we would define an operation on just functions. And we had this other thing called composition. So there were some new operations. Now we have a new operation, the matrix product, that's not quite like anything we've seen before with real numbers, and it doesn't have that commutativity. And function composition, f composed with g, did not equal g composed with f, if you remember. Okay, so that's that. That's pretty much it for section 6.1. You have to learn how to do the 3 basic operations for matrices. So I'm just going to work through some examples or some problems from the homework. So number 1, you have to do -1, 2, 4, and -6, 1, 0, -2, and 5. So again, with addition, you're just matching, right? This element goes with this element. So -1 and 1 Let me write it over here. Gives me 0. 4 and negative 2 give 2. 2 and 0 gives me 2. Negative 6 and 5 gives me negative 1. That's my answer. Alright. And I don't want to bore you with any more than that. I'll do number 11, the matrix product, which I think maybe are these take a little more getting used to. Okay, so always ask the question with a matrix product, can it be done? I mean, you should ask that with any matrix operation, but it's not quite as obvious when you're first doing it with the matrix product. So 2 times 3, yes, it can be done. I'm sorry, I didn't even answer the question. Yes, it can be done. This is a 1 row by 2 column matrix. This is a 2 row by 1 column matrix. So these numbers match, so we can do it. So let's do it. And we're going to end up with just a number. So this is 2 times 3 plus 4 times 1 is going to give me 10. So that's my answer. And you could say that's a 1 by 1 matrix. It really is just a number. Okay. Number 13. 3, 4, negative 1, negative 2, negative 1 and 2. Can we do it? First question. 2 by 2, 2 rows, 2 columns, 2 rows, 1 column. Yes, we can do it. What do we end up with? We end up with a 2 row, 1 column matrix. So it's going to be like this. This first entry here is going to come from this times this. So 3 times negative 1 is negative 3, plus 4 times 2 is 5. Negative 3 and 8 is 5. This times this is negative 1 and negative 1 is 1, plus negative 2 and 2 is going to end up being negative 3. That's our answer for that. Alright. That's pretty much it. I don't want to bore you by blabbing too much, so that's it.